And up next, we have Jeff. Your slides are all up.
A side comment on the Postgres conversion. It almost worked, but then I spent like several days debugging the Postgres. So don't do it if you don't know the database language, like I didn't. Because OpenAI gets it like 95% of the way there, but then the last 5% is very tricky. Nonetheless, it is the future way, I think, of supporting these multiple database platforms. All right, so I'm going to talk about loyalty cohorts, and a lot of this stuff dovetails with what Griffin was talking about, not the concept of loyalty cohorts, but how it fits into our digital twin package. So I will be able to save us a little bit of time. The list of people on the screen are the many of us who were involved in the loyalty cohort software development and the initial study that we published about a year and a half ago. So an issue in doing research with electronic health records is you have poor data completeness. Patients go to multiple healthcare institutions, and those healthcare institutions are not linked together. So that leads to bias in analytics and underestimating disease prevalence and treatment effects. So this person might go to all three of these healthcare institutions. This person might go to those two healthcare institutions. And then if health system C has only their data and they do a study of the patients, say they're studying rheumatoid arthritis, but they go to a rheumatologist at health system A, then they wouldn't have any data on that. Maybe if they have a primary care doctor, they'd have a diagnosis code, but not much else. So the one method to deal with this is to try to find those patients and eliminate them from your cohort and not use them in your research cohort. And that's a concept that's been around for some years, and that has, the term has been coined loyalty cohort, patients with high likelihood of complete data. So Josh Lin at Harvard School of Public Health published a few papers and which led to this validated regression equation that uses 20 proxy variables to predict completeness, including healthcare utilization metrics and preventative care. So we took that algorithm, that regression algorithm, and turned it into SQL code and meshed it with the ENACT ontology and I2B2. That is an old URL, but that is, in fact, our paper. So if you look at the 20 published variables, these are very high-level variables. On the left, the unbolded ones are a lot of utilization metrics, like how many like ED visits, did they have multiple inpatient stays, outpatient stays. And then on the right and the bolded ones on the bottom of the left, those are mostly routine care. So if a patient is getting their mammographies or their PSA tests or their A1Cs at that institution, then probably they have a primary care doctor at that institution. So you'll definitely have a little bit of information on all the patient's conditions, and it's likely, because of the way referrals work, that you'll have a large amount of the patient's data. And you can see from these 20 variables that it's not for kids, because kids are not like under 18, are not getting pap smears and PSA tests. So the algorithm actually, we had to limit it to over 18, and it does, I think, it is slightly biased toward older folks. So we mapped those 20 high-level conceptual variables into ENACT codes using the wonders of the ENACT ontology, and we could map folders of codes to these variable concepts. And we expanded these 20 variables out to 418 codes in a variety of terminologies: HCPCS, ICD-LOINC, CPT. And so it worked like this. For each patient in the medical record, in I2B2, we compute a loyalty score using that regression equation. We multiply the coefficients by the flags, and we get pieces of a score. We add those pieces together, and each person is assigned a loyalty score. And then we can pick a threshold, and anyone above that threshold is considered loyal. So the loyalty cohort manuscript, we used 2 years of data at 3 sites. It was MGB, Pittsburgh, and Kentucky. And we computed a loyalty score based on the 20 proxy variables. And we validated it. And we validated it with the silver standard. So similar conceptually to what Griffin was talking about with Kessler and COMAP, where silver standard was a 1-year follow-up. So within the year, so we looked back 2 years to compute the loyalty score. And then, but we started in the past. So we started like 3 years ago. And then we looked forward a year and did that patient reappear with an actual visit in the record. So that is not a proxy of complete loyalty, but it is a proxy of some loyalty and some utilization of that hospital system. So that was our silver standard, and we were able to get a performance of 0.77 AUC and 0.81, jumped up a little bit after retraining the weights at each site. So not a dramatic change from retraining the weights from the Lin regression equation, but it did help a little bit. And you don't need like a 0.98 AUC for something like this because you're only eliminating problematic patients. So eliminating a few patients that shouldn't have been eliminated does not mess you up statistically. Then this cut the loyalty cohort down into about half the size of the original cohort. And if you look at the data, it did not cut the data down that much. I think it still was like 75% of the data because we were eliminating patients without much data. This is very small on this screen, but you can see the utilization metrics were up there as top things. The higher, the better, as well as some of the routine care. So this is in the digital twin package that Griffin was talking about. What is in the digital twin package is the version that is trained with Lin's original regression equation, so the 0.77 AUC. The system is configurable. You can put in different regression coefficients very easily. We have the R code to retrain on your local data, and we have the SQL code to compute against the silver standard. Haven't integrated that into the digital twin package yet. People are interested. I'm happy to take some time to do that. It is actually in that other GitHub, but not the official digital twin GitHub. So we create 3 new tables: loyalty result Charleston, loyalty result summary. The middle table is because the loyalty cohort, as a bonus, also computes the Charleston comorbidity index and 10-year survival probability. So the algorithm excludes patients without visits and patients under 18 and deceased patients, and then it computes the loyalty score with the regression equation. The Charleston comorbidity index is done in a similar way, the index and the survival probability. And then you get this data on every patient. You get a set of flags you can see at the bottom. Did they have records of medication use at least once or at least twice? That's med use 1 and 2. Did they have a PAP test, a PSA test, and so forth? This is probably not the way people want to look at it, and I do actually have this represented as with with Griffin's work as a I2B2 ontology. So you can actually query these flags and find cohorts of patients that have flags or scores above certain thresholds. The slide for that did not make it in here, but I'm happy to show it if people are interested offline. Then there's the loyalty result Charleston table that gives you all the individual flags for the Charleston comorbidities. This is very similar to what's already in the ENACT ontology that has Charleston comorbidity flags, but it also gives you the score and the 10-year survival probability, which I think is valuable. It's all configurable, so it ships configured for the ACT ontology and the ACT paths, but you can use any ontology you like and just change the change the path in the configurable table. And similarly, you can, the Charleston codes use a code lookup with ICD prefixes and whatnot, and you can change those patterns that it looks for the codes. I think Griffin showed these URLs. You can download the digital twin package and get documentation on installing it. I would like to kind of wrap up some of the work that I've been doing, get the ontology out there, get the retraining out there, and in the coming months. And if people are interested in that, I'd love to chat with you and hear more about how this could be useful to you. So that hopefully was 12 minutes. Okay, good. I did not take my full 15. That is the end. Thank you. Take a couple questions? Sure. Couple questions? Yeah. Couple questions.
So this is a question for Jeff and Griffin, and if it's something that we should talk offline, please let me know. Mm-hmm. So I have a question about my institution, our Mayo Clinic. We have 11 million patients on our medical records, mm-hmm. but our local population is 100,000. Mm-hmm. Okay. Meaning that most of our patients come to Mayo Clinic for more complex care. Okay. Jeff and Griffin, what would you suggest that we adjust the either the loyalty cohort or computational phenotyping based on that kind of a unique circumstance?
So the issue you're concerned about is that the population is small.
Yeah, because most of our patients come from other locations, remote locations,
right,
even international.
Right.
So we're kind of a unique situation.
Yeah.
Where our patient cohort is very big, but
yeah.
our local population is very small.
Yeah. Yeah.
So any suggestion how we need to adjust our maybe algorithm to compensate for that? Is that possible?
So you probably would think intuitively then that your loyalty cohort is just that group that that you have the 100,000 patients, right?
Yes, but we do have repeat patients from remote locations.
Mm-hmm.
We just don't know, what's the distribution and stuff.
Yeah. I'd be interested to see what happens if you run just the out-of-the-box regression equation on and see if it's able to select those patients plus a few others.
Okay. Yeah, maybe we can chat offline.
Yeah, let's chat offline about that.
All right, thank you.
But Griffin might have a comment too.
Yeah, I know the loyalty cohort algorithm has been validated at several sites, but you don't really know how representative your site is to these others. So when I've done this at Beth Israel, I said I actually did not use the loyalty cohort algorithm. I used a much simpler method of just looking for patients with 3 visits as a potentially less biased way of doing the initial filtering. I think it works better for, in my case, for generating the phenotypes, but the that negative use case, like I want to find patients who don't have some condition. I think the loyalty cohort algorithm would be much better for that because I'm capturing with those 3 visits patients who were at Beth Israel for 3 times, but also may be receiving most of their care at another institution. So it depends on a little bit how you use that. I had a different study where I created loyalty cohorts in a different way that wasn't based on specific diagnosis codes like mammograms or other tests. It was more on where patients lived and distance from hospitals and things like that, and factors like whether or not you're in the same state as the hospital and the age of the person. Some of these were important factors in that model as well. So the 20 or so proxies that Jeff had are good in certain circumstances, but you can use different sets of features and proxies to do the same kind of thing, and those may be better or worse in different hospital scenarios. I think there's a lot more research that needs to be done in the best way of figuring out who are these loyalty cohort patients, and then also how loyal do they have to be. Like if you're interested in a cancer phenotype, as long as they're getting the cancer treatment at your institution, you may not care if they're getting treatment for something else at a different institution. So this is step one out of this, but a lot more has to be done to improve on these methods.
Okay, all right, thank you.
I have a question. So can I ask, when we define the loyalty score, do you have a very specific threshold how to define it? And I've been thinking about that after COVID-19, the composition of patients changed a lot. But how do you think about we can should we consider about this? I mean, this kind of progress or threshold should be changed within the time, or could you please share some experience, or what do you think about in the future?
Yeah, so I'm trying to recall the study that we did, and we did choose a threshold for the original regression equation. We used a predefined threshold, but then for the retraining, we also dynamically chose a threshold based on the silver standard. And I don't remember the algorithmic details of it enough to be able to articulate it to you right now, but you can talk to me offline and we can talk about that in more detail.
I actually have a question for Griffin. Yes, I think in the phenotype discussion you mentioned about the base cohort need to have some minimum utilization. So that usually indicate to me that probably it's more appropriate to do chronic disease phenotype. But I noticed on your list you have actually acute respiratory disease or even obesity, because obesity could be chronic, but oftentimes through vital sign or even just observation, you can immediately tell a patient is obesity. I don't think it has like a lot of opportunity. You put in a differential diagnosis for obesity that was misclassified. So question is, how did you even derive and what's the significance of phenotyping on acute respiratory disease?
Yeah, I mean, we looked at very few conditions so far with the manual review, but certainly chronic conditions worked a lot better than acute conditions for that exact reason. So we looked at like chronic renal disease versus acute renal disease, and chronic worked great, and acute was not good at all. Acute might be better just looking at laboratory tests or other clinical factors, whereas there just may not be enough information to build these computed phenotype models. This is kind of a one-off thing. I think that's a really interesting question. If you looked across all different diagnosis codes or diseases, which ones, again, work well with the raw code? Where do phenotypes work well? Where do you need other things like laboratory tests? We haven't looked systematically across all medical conditions to understand where these things work well or don't. We know one-off diseases that we know myocardial infarction has challenges with the phenotype, so we know one-off diseases for different things, but we don't know broad categories of types of conditions that either work well or don't work well with these models.
Got it. So we're kind of exploring where we draw the line, what works better.
Yeah, as more institutions do this and we do more chart review, we get a better picture of this. In the little that we've done so far, I know that difference between chronic and acute, but I don't know if that's a generalizable statement.
Okay, thank you.
Any? Okay.